Syzygy episode 21, BepiColombo blasts off for Mercury. And welcome back for another edition of Syzygy. This time around, we're ditching the black holes that we talked about last time. Last time we went right to the centre of the galaxy in order to take a picture of the huge, supermassive black hole right at the centre of the Milky Way. This time, we're going somewhere a little bit closer to home. We're going to go to the inner part of the solar system and going to have a bit of a look at Mercury. Or rather, we're sending a new little messenger up there to have a look for us. A little satellite, would you call it? A spacecraft known as BepiColombo. So we'll have a bit of a chat about what is my co-host's favourite planet in the solar system. Emily, welcome to the show.
Hello.
Why Mercury?
Mercury, yeah. It's an unusual favourite planet, but that's kind of part of the fun, isn't it? It's always good to be a little bit of an outsider.
I mean, I think if you were to ask most people, this is a completely unscientific poll that I've done of no one, but I would think that if you were to ask people, what's your favourite planet? Most people would say, well, Saturn. Because of the rings, or Jupiter because it's big and it's got a spot, or something like that.
Or some people say Earth because, you know.
Yeah. I mean, close to home. Some people might say Pluto because of the whole Pluto thing.
Yeah. Nobody said that before the Pluto thing.
No. And then everyone went, oh, Pluto. Where were you before? But Mercury, I think fewer than 1 in 8 people would say Mercury. Considerably fewer. I'm going to go out on a limb here. If you disagree with me, by the way, feel free to get in touch. Those of you out in listener land say, oh, Mercury, all the way. But Emily, why Mercury? What's so cool about Mercury?
So part of the reason why I love Mercury is because it isn't Saturn or Jupiter. You know, it's a little planet that can in the solar system. But a big part is actually my own personal education. So when I was just entering university and I was doing, I think it was my first year of studies, and I went into a course which was one of my favourite courses of my entire degree. It was taught by who ended up being my PhD supervisor. And we had an essay to write as part of this course. And we had to write on something that was a current space mission, or something that was going on in the planetary solar system part of the world anyway. So I wrote about Messenger, because it turns out that Messenger was launched that exact year. And I found out about this planet Mercury from what we were going to learn from this brand new Messenger probe. And ever since then, I've followed the Messenger mission and just loved all the amazing detail, because before Messenger, we knew almost nothing about Mercury. We had very little in the way of nice pictures. And then it sort of just blew open this entire world that we had no idea was like this.
Now, without wanting to give too much away at all about, how old you might be and how long ago your undergrad might have been, when did Messenger go up? When was that launched?
So it was launched in 2004.
2004, and got to Mercury in 2011.
Yep, that's right.
I believe.
Yep.
And it was due, or it was scheduled to last a year. And as NASA is tending to do these days, which is big thumbs up to them, the mission lasted a bit longer than that. Went for about 4 years.
Yeah, so 2015 was when the Messenger mission stopped after an incredible 4,000 orbits of Mercury.
And it only stopped because it ran out of fuel. And fuel was, fuel's the hard part of any space mission. It was about 50% or something of the entire weight of the spacecraft when it first went up. They had to take a lot of fuel with them to get there and to keep in orbit. And eventually they just ran out.
Yeah. And you need fuel to continually correct your position in the orbit. I mean, an orbit would be stable, but unfortunately Mercury goes around this big thing of the sun.
Yeah, quite close too.
Yeah, and it's not a circular orbit, as we're probably going to talk about. It's got this weird elliptical orbit. So, you have to keep making these tiny corrections to stay in orbit around that planet.
And so eventually, when you can't make those corrections anymore, you're in trouble. And as the Mercury spacecraft found, when you're in trouble and can't correct your orbit anymore, and you're traveling at something like 14,000 kilometers an hour, 4K every second, and you're getting a bit too close to the surface of the planet, you end up leaving a bit of a scar on the face of Mercury. And that happened sometime in 2015. They said goodbye to Mercury. And it
purposely deorbited crashed, smashed
Yeah.
into the planet.
Yeah, there it is. And so there's now apparently about a tennis court-sized crater, which is the final resting place of small bits of Mercury scattered across a large area.
Which will be quite interesting to spot, given the rest of Mercury is covered in craters as well.
Could be a bit hard to find. Yeah. So we're going to be talking about Mercury today and a bit about what makes it such an interesting planet and this really interesting and quite fun-named mission, which is on its way, winging its way down towards Mercury as we speak. So where shall we start?
So, well, we're talking about this week because BepiColombo launched last Friday, actually, just before we recorded our last podcast, in fact. So it went up on this Ariane rocket. It was sent up from South America. And it's a wonderful mission because it's one of these great collaborations between ESA and JAXA.
So ESA being the European Space Agency and the Ariane rocket being the European Space Agency's sort of large rockets to head up into space. This isn't the NASA rockets. These aren't the SpaceX and so on. This is a completely different group, the Ariane group.
Yeah. So, and JAXA is the Japanese Space Agency. So they could sort of combine forces to put together this mission, which has two quite distinct components. But because Mercury is a really hard planet to get to, they're using each other piggybacking on using the same mission to get there.
And this is the first time that either of them have been to Mercury, isn't it?
Yeah,
I mean,
that's right.
NASA's been before, as you said, with the Messenger mission. But this is the first time ESA and JAXA have been. So that's really cool. And it launched last Friday, and it's called BepiColombo, which is a great name.
It's a great name, yeah.
Unusual, I think, in spacecraft and astronomical terms, having such a fun name.
Yeah, you told me you had to do a little bit of digging about this.
It's Giuseppe, shortened to Bepi. Giuseppe Colombo was an Italian astronomer and space guy who died in the 80s, born in the 20s, died in the 80s, and he was responsible for a lot of the work that went into, what was it called?
Gravity assist.
That's what it was. Yes, gravity assist, which is where you, in order to maneuver a spacecraft from the Earth to close passing by other places in the solar system or to get it into orbit around a particular planet, it's really difficult. You could get to Mercury in a couple of months, right? If you just launched from Earth and went, we're going straight down towards Mercury. Trouble is, you've got the sun, large amount of gravitational pull going on there. You're going to speed up a lot. And so, you'll get to Mercury in a couple of months, and then you'll just go whipping on past at very high speed, going, and Mercury's been left behind, and poof, into the sun. So you need to do it a little bit more carefully than that. And one of the ways to do that is by using a bit of an assist in passing by, doing a flyby of Earth again. I think BepiColombo is going to do a couple of passes by Venus, and eventually, slowly, carefully approaching Mercury at a reasonable speed to actually be able to get into an orbit around it, rather than just whipping past at speed. And Giuseppe Colombo, was one of the people instrumental in coming up with that idea and figuring out how it works, which is very cool.
Yeah, and this is why going to the inner planets is so much harder, at least in terms of getting there, than going to the outer planets.
Well, I mean, the getting there isn't the hard part. The staying there is the hard part. Like I said, you can just fall towards Mercury. That's not a problem. It's stopping your fall.
Yeah, at a reasonable speed.
Yeah.
And of course you could do that by doing back thrusters and things like that, but you'd have to carry stupidly huge amounts of fuel.
Ridiculous amounts of fuel.
It just becomes really hard.
So the clever way is to do a couple of flybys of planets along the way to grab a bit of momentum from that planet as you go past, to get into its gravitational pull, to just slow you down and send you off in just the right direction, at just the right speed, to just gradually edge your way into the orbit that you want to be captured by Mercury, rather than just whipping past it at speed.
It's the same thing for every orbit. If you want to orbit anything at a particular distance, and you have to be going at a very precise speed to enter that orbit.
Yeah. It's not like science fiction. It always makes me grimace a bit when I watch something like Star Wars or something like that, when they just say, all right, we're just going to pop over to this planet over here, and you just fire the thrusters and over you go, and then just pull into the parking lot down on the planet. It's like, no, you're going to be really going way too fast to be able to do that. It's not going to work. But that's why it's fiction, I guess.
So it's going to take good old BepiColombo 7 years to get to Mercury. It's going to do Earth flybys, as you mentioned. It's going to do Venus flybys, and it's going to do a Mercury flyby as well before it actually goes into orbit.
So this is a very careful orbit, a very careful trip being planned out. I mean, what did you say, 7 years to get there?
2025.
As opposed to the direct line of flight as the crow flies, you could do it in a couple of months.
Yeah,
but
4
this
months.
is 7 years, which is, that's a long way to go.
Yeah.
But like we said, do it right, and you can actually get in orbit around the planet.
So because it's hard, you get a friend.
Yeah.
And you put your instruments together.
Exactly.
Which is what ESA and JAXA did. So there's two quite independent parts to this mission. So the ESA part is called MPO, which is the Mercury Planetary Orbiter. And that's kind of focused on what's the planetary surface like and making measurements to do with using radar and those kinds of techniques to look at what surface features are going on. And there's JAXA, who's looking at a really interesting part of Mercury, which is its magnetic field. So they've got MMO, which is the Mercury Magnetospheric Orbiter.
Very nice. Very nice. So, I mean, it does kind of raise a question, which is, so why are we doing this? I mean, if you were to say to me, Mercury, is it an interesting planet or not? Is this worth spending a lot of time and a lot of money going there? I mean, any space mission can be interesting. But I would have thought that Mercury, look, it's just this small lump of rock very close to the sun. It's been, burnt by the extreme heat of its orbit, and anything interesting surely has been burnt off. It's just basically the moon, isn't it? Orbiting down close to the sun. Why are we so interested in Mercury?
So a really big part of why Mercury is such an enigma is it breaks all of our solar system formation theories.
Ah, okay. So going from this is a trivial lump of rock to, no, this breaks it all. This changes the rules.
It shouldn't be where it is doing what it is given what it's made of, basically.
Okay. So take me through that then.
Okay, so the really big thing about Mercury, if you're going to remember one fact about Mercury that makes it weird and unusual, I think, is that it's got this huge core. So the core of the Earth accounts for something of like a couple of tens of percent, maybe 17% of the volume of the Earth. And, we've got this liquid iron core, and it does things with our magnetic field and so on. The core of Mercury is about 60% of its mass.
Wow. So it's huge.
It's huge. And there's only just a very sort of small mantle and crust on top of that.
So Mercury is basically mostly core.
Mostly core.
Right.
Not sure why. It probably shouldn't be. And that core is iron. So
and that's
magnetic.
To be clear, that's unusual. Like it's not like the Earth is unusual.
No,
in
the
having
Earth
a small
the Earth
core.
is standard, right?
Right.
In this case.
Okay. So Mercury's the weird one.
Yeah.
I mean, it almost kind of sounds like Mercury should be bigger if it's got a core that big.
Exactly. So why isn't it bigger?
Right.
Because of its, and we'll talk a lot about its orbit, I think, when we talk about the characteristics of Mercury, but because of its orbit is weird, and because of this huge iron core, it's kind of like it doesn't really fit with how we think the solar system formed. So we think that we have these wonderful sort of models and theories about how you have a protoplanetary disk which forms at the sort of same time as the star forms. We've seen lots of these disks and around other stars forming, and the planets even forming in them. There's some beautiful Hubble images of planets, like baby planets forming around, at least protoplanetary disks forming around baby stars. And there's kind of a mass distribution, and you get the rocky things that sort of start to stick together first, and then eventually you get primordial atmospheres that stick to the largest rocky things, and then you get gas giants which form out beyond what we call the snow line because it's too cold for some of these gases to exist. Anyway, but then how do you make a really big, heavy lump of rock right at the center, right close to the sun, that has a bizarre orbit?
Sounds like we need to unpack this orbit a little bit. So tell us about that. Mercury doesn't just go in a close, tight, circular orbit around the sun. It's doing something a bit weird.
No, it's got the most eccentric orbit in the solar system.
Okay, now eccentric means something quite specific here. It doesn't mean that it's just wild and weird.
Yeah, it's not got a top hat and a mustache.
Although that would be cool too. No, in this case, eccentric for an orbit means that it's not close to being circular. It's much more elongated, right? All orbits are ellipses, which is a specific mathematical shape, and the sun is at one focal point of that ellipse. Some planets have very close to circular orbits where it's basically, the sun is at the very center. But other orbits are much more elongated. And so sometimes the planet comes past closer and sometimes it's much further away. And you're saying that Mercury's got a very elongated orbit.
Yeah. So the average orbital distance of Mercury from the sun is 0.4 astronomical units.
Okay.
So 0.4 times our distance to the sun, 40% of the distance.
So that's average.
That's average. But it changes by, from say, between 2/3 and 1 of its maximum.
Okay.
So its orbital distance changes by 1/3.
That's quite a lot.
It's quite a lot.
So in other words, sometimes it's much closer than at other times.
Yeah. And that means that all sorts of weird and wonderful physics start happening with orbits. So, for example, if you're in a circular orbit, you travel at the same speed for the whole time that you go around that orbit. If you're in an elongated orbit, then you travel faster when you're closer to the sun than when you're further away.
You can think of it a little bit like falling down into what they call the sun's gravitational well. The further down into that you go, the more speed you pick up. And then as you swing around the other side, you slow down. It's kind of like a swing going backwards and forwards. As a swing is going up to its highest point, it slows down, comes whipping back through the middle again, up to the other side. Orbits are a little bit like that. Fast when you're close, slower when you're further away.
Yeah, this is known as Kepler's third law. So
good old Kepler.
Yeah, good old Kepler. But that also introduces some interesting gravitational effects because the sun's gravity is stronger when it's closer to, when Mercury is closer to the sun. And so Mercury has entered this resonance orbit where it is tidally locked itself to the sun.
That's tidal as in ocean tides as opposed to tidally, which is neat.
Yes, that's right.
So it's not neatly locked, it's tidal.
Tidal, yep. Yes. Yeah, that's right. So what that means is that there's a relationship between how fast the planet is rotating and how fast it's orbiting.
Is this a bit like the moon?
It's exactly like the moon.
So... And I'm embarrassed to say, I actually didn't know this about the moon until I was doing my undergraduate degree. I just never really figured it out and thought about it very much. But when we talk about the dark side of the moon, the moon, when it goes around the Earth, we only ever see one side of it. And as it rotates as it orbits around the Earth, it is also rotating on its axis. And those two motions, its orbit and its axial rotation, are locked so that we only ever see one side of the moon. And you're saying Mercury's doing the same sort of thing with the sun.
Yeah. So with the Earth and the moon, we have what we call one-to-one tidal locking. So that means that the moon rotates at the same rate as it orbits. So one orbit is exactly the same length as one rotation.
And the thing that I hadn't figured out until embarrassingly late in my physics career was that that's not a coincidence. There's a reason for that.
That's gravity.
Yeah.
That's kind of like the minimum energy orbit that you end up in. And you can do that you can only do that if you're shedding energy. And it turns out that the moon Earth system, you shed energy through friction with tides and that sort of thing.
Yeah. And I mean, I think probably the reason why I hadn't thought about it, just in my own defense, is that when you're studying physics, the things that you tend to study first are idealized situations. And so you treat the moon as a point object and you treat the Earth as a point object and you work out what the forces are and so on. But the moon isn't a point object. It's a big, round, blobby, rocky thing. And so is the Earth. And when you have those kinds of situations, then gravity's not simple. And you can actually have effects like these tidal locking mechanisms that mean that things get joined together.
And I don't think you should feel too bad about that either, because
thank you.
I don't think it's a very obvious thing that the moon rotates at the same rate as it orbits. I've had dinner party conversations with beer bottles and oranges and all sorts of wonderful things, trying to move things around and spin them at the same time. And it is a difficult three-dimensional concept to wrap your head around.
Oh, thank you, Emily. I feel much better about that now. So back to Mercury then. You said the moon is in a 1-to-1 ratio for its tidal locking with the Earth, which is why we only ever see one side of the moon. It does one orbit and one rotation. Mercury is different.
Mercury is really, really unusual. It's got a 3-to-2 resonance with its tidal locking. So what that means is that it spins 3 times exactly for every twice that it goes around the sun.
Cool. Okay.
So this is fascinating because first of all, it can't really happen in, let me say, an idealized situation. If we had a solar system which was just Mercury and we had no other gravitational effects from anything else apart from the sun and Mercury, you can't achieve this orbit.
Right. So it's doing the impossible. Is that because of the influence of the outer planets then?
Yeah, and possibly the way Mercury ended up in its orbit to begin with as well.
Okay.
So there's a few things going on there, but because it's eccentric as well, and it's only the eccentricity that maintains this of the orbit that maintains this 3-to-2. Otherwise, it would be 1-to-1. So it's really, really quite cool. That sounds like that's just a mathematical anomaly, and there's only things that like really nerdy astronomers are going to get
all the
into.
astrophysicists are really getting off on that, but otherwise it's who cares?
But
seriously.
Let's start to think about what that actually means if you were to live on Mercury.
Okay.
So we define a year by how long it takes to go around the sun, right? So a year on Mercury is about 88 days, or 88 Earth days.
Okay, that's pretty short, but I mean that's what happens. The closer you are to the sun, the faster you're orbiting.
Yeah. And so we define a day by how long it takes for us to spin once on our axis.
Yep.
And so Mercury spins quite slowly because it only does it 3 times for every twice it goes round. So it takes 58 Earth days to spin around.
So, I mean, 3 days for every 2 years. That's 1.5 days a year.
Well, it turns out that's even more interesting than that, because imagine as you're moving around, if you're rotating very, very slowly, the position of the sun changes as you go around, right?
Yeah.
So you're going around really, really slowly. So although it takes you 58 days to spin, actually a day in terms of what we define as a solar day. And
so the sun actually going across the sky.
Yeah, so the sun returning to exactly the same point in the sky takes 176 Earth days.
Oh, wow. That's a really long day.
That's a really, really long day, which means you have one day every 2 years.
Ah, and if you're that close to the sun, that's got to get really hot.
It's really, really hot.
Wow.
But a day is longer than a year. That's a cool thing, right?
That's weird. Is there anywhere else in the solar system that does that kind of thing?
I don't think so. I might be wrong, but I don't think so.
Wow.
I think Mercury is pretty special there.
Okay, Mercury's weird. So half of the planet is just baking away. And I mean, we're talking really hot temperatures. We're talking like over 400 degrees C, right? And on the shiny side of the planet, for really long periods of time.
Really, really. That's why it gets so hot, because you got such a long day.
Wow.
Yeah, that's one of my reasons why I really love Mercury as
That's
well.
very cool.
That's
very cool. So there's really interesting dynamics going on there.
So you've got your 450 degree Celsius daytime temperatures. Still not quite the hottest planet in the solar system. Venus, of course, with its greenhouse effect.
Yeah, so
trumps
Venus has got an atmosphere, and it's the terrifying model of the greenhouse effect here on Earth. Venus is the one that we look at and go, okay, let's at least pull back before we get that far.
Yeah.
Venus is baking because it's closer to the sun than we are, but it's also got this crazy runaway greenhouse effect that takes its temperature way, way, way up. Whereas Mercury, all of it, any atmosphere that it might have is presumably just completely boiled away by now. And so it's got none left. It's just pure baking factor from the heat of the sun, getting up to 400, 450 degrees, which is hot enough, thanks.
Really, really hot. But then the other side of Mercury can get down to minus 180 degrees.
Seriously?
Cold.
So
really cold.
I mean, in a way, it's kind of lucky that it's got such a long day-night cycle, because going between those kinds of temperature extremes, the planet would just shatter if it was spinning faster than that.
Yeah.
Wow.
It's a very, very cool planet. And actually, one of the cool discoveries from Messenger was that they found water ice on Mercury.
Sorry, where?
Deep down in some of these craters that never get the sun.
So there are bits which are always in the shade, presumably up near the poles or something, which are always in the shade, and they've got water ice in them.
Despite it being the closest planet to the sun.
That's just nuts. I'm imagining these little bits of water ice just going, just don't go over there. It's just, wow, that's amazing.
Super, super cool. And the reason why we have all these why we can have water ice is because you have shade. So the shade has to come from something. Mercury is not a smooth marble spinning out there in space. It's actually a really interesting deformed planet, right? And what part of that formations and the interesting geological structures that you can see, some of them are called wrinkles.
Ooh.
These are really cool. So what's happened is that Mercury has shrunk.
Right. Okay.
Because of the cooling down process when it formed, or as we'll talk about, where something happened to make it shrink. It cooled and it shrank, but it only had kind of rock. It doesn't have like molten stuff, and it didn't shrink very slowly. So what that means is from the shrinkage, you get these kind of wrinkles up on the surface, which turn into huge cliffs that are several kilometers high on the surface of the planet.
That's amazing. Actually, it's funny. It just reminds me. I made a tray of brownies last night, which I should have brought in. Actually, that was remiss of me, wasn't it? Sorry. But my point is that when you make brownies or when you bake a cake in the oven, right, when it's really hot, the top is nice and smooth. But as it cools down and it shrinks, then it wrinkles. And this is a similar this is like a big Mercury cake.
And the proper term for them is wrinkles.
Nice. But kilometre high, several kilometres high.
Yeah.
So big.
Exactly. And Mercury has one of the oldest surfaces in the solar system as well, because it's got all these beautiful craters. I mean, the images that Messenger sent back just blow my mind.
They are amazing.
Gorgeous.
Yeah, we'll put some links to those in the show notes.
Yeah.
But what do you mean by oldest surfaces? Like surely all of the planets have old surfaces.
If you have an atmosphere, or if you have geological processes like volcanoes.
You mean the oldest surviving surface features?
Yeah.
Right.
So those sorts of things, water, weather, volcanic eruptions, whatever, they erode top surfaces away. So Earth, you don't see many impact craters from the early solar system on the surface of Earth because those things have gone in the last
washed away, they're blown away.
billion years, right?
Yeah.
But Mercury has just kind of sat there. It might have had a little bit of volcanic activity at some point, but pretty much for the last 4 billion years or so, not much. So it's just been hit and bombarded by impact after impact after
over
impact.
Millions and millions of years.
And so you get craters within craters within craters within craters. It's really, really cool.
Yeah, some of those images from Messenger are just amazing. So, I mean, can't wait to find out what the ones from BepiColombo look like.
Yeah.
Got a few years to wait, though.
Yeah. Same thing with the moon, though, incidentally. That's why you see lots of craters on the moon.
Yeah, same idea. No atmosphere, no water sloshing around. So, something hits, it scar stays. Yeah. So let's go back then to Mercury and its origins, because it sounds like there's an interesting story there. Mercury's weird. It's got this huge core. It's in this weird, tidally locked orbit.
I got one more fun fact about the orbit first.
Okay, all right. I'm
I
jumping
want to do it.
I'm jumping the gun. All right,
okay,
come in.
Because this is actually
got?
something that I learned pretty recently. All right, so one more really cool thing about the weird orbit spin of Mercury is that you get an interesting effect where you have at some points in its orbit, its speed of rotation gets a little bit faster than its speed of orbit.
Okay.
These are angular speeds, but basically it's going to be spinning a little bit faster than its orbital speed. And what that means is if you were to stand on some places on the surface of Mercury at some particular points in its orbit, then what you would see is the sun rise halfway up and then it would go straight back down again. It would set again without you actually having a day.
So because there's the year and the day times are comparably so close, you can get sometimes in the orbit where its spin is a bit faster.
Yeah, because
so
its orbit slows down.
The sun comes up, and then the rotation of the actual planet goes, no, back down you go.
Yeah.
And we'll try that again next time.
Yeah, and that whole process
Weird.
takes about 4 to 8 days or something
Weird.
like that. Yeah. That's a fun thing, right?
Yeah. So
I mean, we talk
okay.
about exoplanets that are just these worlds that are inconceivable, that might have all these wonderful things, but
close to home, Mercury is a bit nuts.
yeah.
All right. Okay. So we've established then, without a shadow of a doubt, that Mercury is an interesting and pretty weird place. It's eccentric in more ways than one. So where, Emily, did it come from?
Good question. We have 3 possible ideas.
Okay.
And
Hit
this
me
is
with
one
the
of
first
one of the things that this BepiColombo probe is really trying to nail down. So first one, did it migrate inwards, for example? Was it form somewhere else and actually arrive where it is today? Well, maybe. That's actually not so much a favoured theory at the moment because of the composition of Mercury seems to point on that it's sort of, it kind of makes sense for where it is.
But the idea being that somewhere way back in the earlier epochs of the solar system, it was formed further out and then had a collision with something, got bumped out of its orbit and then wandered closer to the sun and ended up on this weird orbit.
So let's go with numbers here. So number one theory could be that it had this big collision with a huge impact, and that explains why it has such a huge core, because it had more stuff on the outside,
Right.
but a mega collision sort of blew all that stuff
Okay,
off.
so you're left with this big core but much less stuff around the outside.
Yeah, a little bit like what we think happened to the Earth and the Moon.
Yeah.
But the surface elements on Mercury suggest that there's things there that shouldn't exist if it had had one of those enormous impacts.
Right.
So particular sulfur species and things like that, which if you'd had one of those big impacts, they shouldn't be around. And there's not really been any way for those things to arrive on Mercury.
Okay, so nice idea, but doesn't really fit with the modelling that's been done to say, okay, if this, then that. It doesn't really work.
Second theory.
Okay, number 2.
It was one of the first planets to form. It formed really, really early out of the disk when the proto-sun was still really nasty. Like stars being born, and the sentence sounds really nice.
It's a difficult birth.
And romantic, but actually, yes, stars being born, you don't want to be anywhere near that. They are nasty things, right? They have huge flare-ups. There's huge amounts of ionizing radiation. They're just nasty environments.
It's a difficult time.
Yeah. So basically, if we think maybe Mercury formed and then this proto-sun kind of melted the top off it. From its huge outbursts and huge radiations and huge temperature fluctuations. So the outer bits kind of melted / blasted off the surface.
Right. So
of
the sun had a difficult birth, and Mercury just happened to be in the path of that, and also had a hard time.
But that would kind of require Mercury to have been at least a good way through its formation earlier than the other planets. So not so sure.
So could happen. And would that explain its very eccentric orbit?
Potentially, yes. Yeah, because if you have a blast from the sun, it kind of can knock you a little bit onto your...
Yeah.
But the favoured theory, number 3 at the moment, and this is really what they're trying to nail down with BepiColombo, is that what they call the Solar Nebula, so this is kind of the extended sun plus early planetary disk, had some drag in it. So the way we get these rocky bits of planets is that you take small things and you stick them together, right? So you take 2 infinitesimally small particles, they stick together through static forces. You stick. After a while, you get gravity that sticks things together more, and you stick. It's called accretion.
So dust becomes lumps, becomes rocks, becomes planets.
Yeah.
Eventually.
Yeah. So if you have this kind of nebulosity, which is like gas and kind of very small bits of dust and things, then you can cause drag on those things that are being formed, and therefore you can kind of lose off all your lighter particles because it's only the drag of the heavy ones that sort of end up sticking together.
Right.
That's very hand wavy, and I'm not really sure of all the details of that theory.
Okay, so I'm imagining sort of the sun with this large, disk around it of not nebulous material, but something which is actually, I'm imagining almost swimming through it, and you've got these planets starting to form, a very early Mercury, and you're saying that the big lump in the middle forms, and it would normally accrete more and more and more stuff onto it, except that the lighter stuff around the edges is getting blown off by this drag as it's going around through the nebula of stuff around the sun. So where you would normally get a much bigger planet with a much thicker bit around the core, actually a lot of that stuff has just been washed away, blown away as it's dragging around through this soup around the sun.
Yeah.
Interesting.
Because remember, and this is one of the great things that I learned from solar physics, is that we live inside the atmosphere of the sun, right? The sun just doesn't stop at the surface that we see. It has this huge solar wind of particles, and we have this extended atmosphere of stuff from the sun.
Which we don't notice terribly much because we've got, an atmosphere, but we've also got the Earth's magnetic field, which kind of shields us from the vast majority of that. But we do see it on a couple of occasions. We see it in the aurora at the North and South Poles, Aurora Borealis and Aurora Australis, which is where the solar wind, the ionized particles and so on get funneled down towards the magnetic field at the poles, which is cool. That's nice. But we also see it when there's a particularly big flare-up from the sun and the solar wind gets particularly strong, and it knocks out all of our communication satellites for a bit, and everyone goes, modern society collapse.
So imagine all that on steroids when the sun was being formed.
Yeah.
So
yeah.
It would have been a pretty interesting and pretty nasty place.
Okay, so that's the preferred theory.
Yeah.
Right.
So both of the types of measurements, actually, that BepiColombo's probes are going to be looking at will tell us more about this. So we'll learn more about the structure, chemical elements that are on the surface of Mercury. There's lots of measurements of the magnetosphere, whereas Mercury has really overdense spots underneath its surface, which is weird. Don't know why. It's not a perfectly uniformly dense sphere. So lots of these questions that Messenger mission raised and was able to get preliminary data on will hopefully be answered by this new mission.
Excellent. So all we've got to do is wait 7 years for it to get there and start sending back some data.
We will get some cool stuff in the meantime, right? So we're going to get, the Earth flybys are nice because it's always nice looking at Earth from space, right? But Venus flybys are useful as well. We haven't done that for a wee while. So
is it going to be spending much time around Venus? Is it going to be able to take much data, or is it just sort of winging past and picking up a bit of momentum?
Yeah, it'll take some nice pictures, and I think it goes around twice around Venus, so we'll get to see it.
Yeah,
just a few snapshots of Venus.
That'd be nice.
Yeah.
So it in a way, it seems a little bit odd to be talking about a mission which is literally just launched and is not going to be sending back data about its primary target of Mercury for 7 years. But, the whole notion of missions, of sending spacecraft up to go and have a look at a particular thing is actually a pretty important part of modern astronomy and modern space exploration. We've seen a little bit of that over the last little while. I think we reported, was it last week or a couple of weeks ago, about the Hubble Space Telescope, which is a mission which has been going on for a very, very long time, which got into a bit of trouble with some of its gyros. And fortunately, they've managed to give it a little bit of a shake, sort of the Hubble equivalent of turning it off, slapping the side of it and turning it back on again, and everything seems fine there. But it's not going to last forever.
No, and we have to think about how we do science in sort of these long-term scales, because if you think about the current big space telescopes that we have, a lot of them were part of the NASA's Great Observatories program. And this is a program that was conceived and really thought through in the 70s.
Wow, that's going back.
Yeah, that's going back a long way for missions that were launched in the 90s in 2000. So there were 4 great observatories. So we had Hubble, 1990, Compton, which is a gamma ray observatory that was launched in 1991.
Is that still going?
That's the only one that's not still going.
Right.
So that was in 2000. That was basically end of mission.
Right.
Because of a gyro issue. But, still huge, 9 years, and it was well beyond its original mission length still. Chandra, which is X-rays.
Mm-hmm.
So that was launched in 1999.
And that's still going.
19 years old, Chandra.
Pretty good.
So that Chandra had a bit of a wobble a couple of months ago, but that's okay now. And Spitzer was an infrared telescope. So that was launched in 2003. It kind of ran out of coolant in 2009. So it's kind of on a Spitzer V2 mission at the moment. It's still working, but it doesn't do all the things that it originally did.
Got to adapt as these things get into issues or lose some of their capabilities. Well, it's not all over.
No.
We just have to use it slightly differently. But they're still going. I mean, that's staggering,
That's
and that's
15
great.
years,
That's really good. But it is a little bit like, well, my car's still going, even though it does need a new fan belt and one of the doors fell off and it's only got 3 wheels. but it still goes. Eventually you are going to need a new car.
Yeah. So, and these missions take decades to plan and execute. And there's potential for us to have a serious gap in terms of these kinds of observatories. So the great observatories were designed to cover the electromagnetic spectrum in those different regions. We've got some plans to replace or some of these things, but nothing like that particular NASA program. Of course, we've got James Webb, which is kind of Hubble 2.0 in some ways.
And any day now. poor James
March
Webb.
2021.
Yeah.
So we've got to hold on to Hubble.
It'll happen. Come
until
on.
then. That'll make Hubble more than 30 years old.
Wow. And I mean, you can't rely on that.
No.
Literally any day, any week, any one of these great observatories could just fail. And then you're left with, as you say, a gap that you can't fill anytime soon.
So we're kind of in the states of planning maybe one other big observatory. There's about 4 proposals. They're in different wavelength regions. So there's an ultraviolet one and an optical one, and et cetera, et cetera. But they're not planning those to launch until 2035.
Wow. So these are long-term mission goals.
Yeah. So we need the stuff that's going up now to do like planetary exploration. Because it's not that we need something to work on in the meantime. We've got lots of work.
What are we going to do? We've got nothing to do for 15 years.
But we also, I think, as humanity, need to have new results all the time. We have to have things that are going to inspire the next generation of astronomers, space scientists, engineers, management who are going to look after these space missions. So I think these things like BepiColombo are so important for those reasons.
And that brings us to the end of another edition of Syzygy. It's been fun. I've enjoyed learning about your favourite planet, Mercury. Thank you, Emily.
And I'm hoping to learn a whole lot more about it.
Yeah, we're going to have to wait for a while, but it's going to be good. It's going to be good. Listen, if you've enjoyed listening to the show, then why don't you let us know? There's a whole bunch of ways that you can get in contact with us. You can talk to us on Twitter. Emily, you're the Twitter goddess.
So we are at SyzygyPod, SYZYGY. We'll keep you updated when we're recording, when we're going to be releasing the episodes, as well as all the wonderful things across the Twitterverse that kind of, pull at our heartstrings or tweak our humour, that kind of thing.
Yes, indeed. We'll put up all sorts of links on there. Facebook, you can find us on Facebook. Just search for the Syzygy Podcast. I also believe it's facebook.com/SyzygyPod. I really should look that up one day so that I can stop saying I think it's this and say it definitively is this. But hey, let's go with that. And if you enjoy watching your podcasts as well as listening to them, then go and find us on YouTube as well. There's all of our past episodes up on there in video form because, of course, astronomy is a very visual thing, and so we like to put up pictures associated with what we're talking about. Future episode coming up. This is going to be an interesting one. On Saturday, the 17th of November, we're going to be recording Syzygy live in front of an audience as part of York's Your Night Festival, which is an evening of talks and activities, all based around scientific research going on in and around York. So we're going to be a part of that. We're going to be talking about exoplanets. It's going to be great fun. If you do happen to be in the York area, or you just feel like taking a bus, a train, or a plane to come in and visit us, then go and have a look at our webpage, syzygy.fm. We can get all the details about this once-in-a-lifetime live recording of Syzygy. It's going to be great fun. Bring your questions along. It's family-friendly. Bring your kids. Bring everyone along. It's going to be great.
And bring along your favourite exoplanet.
Exactly. Yes. Yeah, bring it along and we can have a look at it and pass it around. It'll be great fun. But that pretty much brings us to the end of everything we can talk about today. As ever, we're producing this episode of Syzygy in the plush office of Emily here at the University of York, and we're very thankful to them for giving us the opportunity to do that. My name is Chris Stewart. I've been joined by Emily Brunston, and we will catch you next time.
See you later. God.
What did you forget?
I forgot the acronym for messenger.
Oh, we'll put it in now. I'll throw it in at the end.
Yes, it's a wonderful acronym because it's not only an acronym, but it's an acronym that makes a name.
Yeah.
And not just any old name. It's an acronym that makes a name messenger, which links to the name of Mercury itself, because Mercury is the Roman god who was the messenger for the gods.
Mercury was the one with the winged feet, wasn't he?
Yeah. Hermes, we figured out was...
So Hermes being the Roman...
the
Greek
version.
one, and Mercury being the Roman one. You kind of get the feeling that they put a committee together to say, we know what the acronym has to be, you guys figure it out. So messenger, what is it?
Mercury.
Okay, M-E.
Surface.
S.
Space.
S.
Environment.
E-N.
And geochemistry.
G-E.
Ranging.
So Mercury, surface, space environment, geochemistry, and ranging. They worked really hard for that, didn't they?
Well, I can let you in on a little secret that astronomers have.
Yeah.
We have acronym generators on the internet.
Serious?
We do.
Of course you do. Of course you do. I can almost imagine them saying, do you know what, can we add another instrument to this spacecraft? Because we really need to get geochemistry into this acronym. So can we just bolt on something and then we can say it's geochemistry? Yeah, done. It's only another 100K. Easy.
It's fine.